All right, so welcome to our AP Physics little lesson on simple harmonic motion. And so what we're going to do is we're going to take a look at some of the conceptual ends of things here. And so what we've got going on is we have a mass on a spring, and this mass is going to be able to oscillate back and forth. Sometimes this thing is just called a simple harmonic oscillator. And typically we're going to use a spring to do that. So this thing is going to start at its zero position here, okay? And in this position, the spring is not applying any force back and forth whatsoever. It's completely relaxed. And so what we'll do is we would pull this box in this direction and then release it. So we pull it to some distance, and then when we release it, it is now going to be set in motion. So when we pull it and we release it, the moment that we release it, it has potential energy. It has elastic potential energy. We release it, that potential energy converts into kinetic energy. And so by the time it gets to, it's released, it gets to here, to the middle, it is moving to the left, it will have kinetic energy. In fact, it will have all kinetic energy. And then it will shift to the other side. And this distance here, x, that it was displaced, you would have an equivalent distance on the other side. So there's just as much displacement to the right as there is to the left. All of the energy would be potential here, and it would be changing directions and shifting back. Now, the force of the spring, as I'm pretty sure we've discussed before, the spring should follow Hooke's law. This here being Hooke's law. I think that's how you spell it. You'll have to excuse me if that's wrong. Hooke's law. Terribly written. So what does that mean? That means that if I were to displace it some distance x, just to give it some arbitrary value, I'm going to displace it some distance x, and then I'm going to displace it even further at a distance of 2x. So what this means that if I displace it x, it takes some amount of force to do that, and the spring would be pulling back in this direction, trying to restore its original position, which is why it's called a restorative force. And if I then go to 2x, the force would be 2 times greater. So it's a linear progression between force and displacement. And as long as this restorative force always follows this linear progression, Hooke's law, then it will follow simple harmonic motion. If it is not linear, then it is not really simple harmonic motion, and that's kind of how things are defined. So it's an oscillating moving object that has a linear, directly proportional relationship between force and displacement. Okay, so let's kind of take a little bit of a closer look at it. Let's look at the velocity, the acceleration, things like that. So when we set this thing into motion, its initial velocity is going to be 0. Its force is at its maximum, and it's going to be accelerating to the right. When it crosses the center, its velocity is going to be at its maximum. We would denote that as v max. And then it is going to get to the other side. Its velocity will be at its minimum, and its potential energy will be at its greatest. And here we have this expression of x equals a. And so all this means is that x is going to be any sort of arbitrary distance or displacement. So it's really just position. So x is its position at any arbitrary point in time. Versus a would refer to when it is at that specific position where it's at its maximum distance. So x max, right, maximum displacement, is the same thing as a, otherwise known as amplitude. And that's the main key there. Okay, whenever you see this capital A for amplitude, that is the maximum displacement. If I just have x, that is just some arbitrary spot. It could be anywhere in between, right? But if it's specifically A, it is the maximum position that it could be at. So that means that if I want to know how much energy there is in this system, and I'll get more to this later. So in fact, let me, so I'm going to express it as the sum of all energies. That is going to equal the let's see, it could have translational energy, right? 1/2 mv squared plus any elastic potential energy. So I'm going to say 1/2 kx squared. Does that seem familiar, right? So 1 half kx squared being the elastic potential energy. Now, when you pull this object all the way to the left, so it is at its maximum displacement of A, then I could say that this is equal to the 1 half k a squared, or x max squared if you prefer, where since we have pulled this thing all the way to one side, in fact we often would denote this as a negative a on this side, and the other side we would have a positive a, right? So one direction versus the other. But if it is specifically completely off to one side, the kinetic energy is 0, it's all built up into potential energy, then of course we can say that that potential energy, when it's at its maximum displacement, is equal to the energy total it has at any other time. And so we can make this expression and then maybe even solve for its velocity at any specific time. If you recognize that if we want to look at the time right here, okay, where we're going to look at its Vmax, then that means that this potential energy has gone to 0, hasn't it? So we can just say that 1 half mv squared max is actually equal to 1 half ka squared, because this would be 0. So let's say that we take a spring, a mass and a spring, and we hang it horizontally. So initially we will take the spring and just hang it horizontally, it's just hanging on its own. And so this is the end of the spring, and I'll just treat that to be my x naught. But then you take a mass and you hang it from that spring and you gently let it down and let it kind of get to its new equilibrium position. Maybe it has to kind of like relax a little bit. And it eventually comes to a stop. What about that new equilibrium position? What a lot of people don't realize is that the total energy of the system is still simply just 1 half mv squared plus 1 half kx squared. You do not have to add in the gravitational potential energy, the mgh. Okay, this does not need to be added in because we had let this object settle in, right? It started at this equilibrium position. So as long as we are considering this spot right here to be my x naught, my initial position, then in that case, I don't have to consider mgh at all. It's already been considered by making this my 0 position, because this is the equilibrium position where it doesn't want to accelerate up or down. I would only consider mgh if I were going off of this position. But why would I do that? That makes things more complex than it needs to be. So we are going to let this thing settle. It's going to have this new equilibrium position. So therefore, the total energy of the system as it oscillates back and forth is just simply the 1 half mv squared plus the 1 half kx squared. All right. I think that's probably all I need to cover on that, because that's the most common misconception on that problem. So let's go back to this idea of the potential energy. I kind of already expressed this, but just kind of look at this little graphic on this issue. So again, on each end you have an amplitude of A, or x max, and so it goes from potential to kinetic to potential, right? Kinetic, potential, potential, kinetic, potential. And here it's somewhere in between, right? It's not completely kinetic, it's not completely potential, it's somewhere in between. So we have to express its total energy as this, and we can determine its velocity at that particular position, right? At this particular position, we can determine its velocity. So just like I said before, its maximum position of A can be set equal to this total mechanical energy. So a big part of simple harmonic motion is just setting this thing in motion and actually just trying to determine its velocity at any point in time. It's at least a small part, not necessarily the big part. The big part with simple harmonic motion actually will come into play with determining an object's frequency. Maybe from the frequency we can determine what the mass is. That kind of thing is where all this stuff starts to come in. But the math gets a little bit interesting, and here's why. It's actually circular motion. If we have circular motion happening here, okay, so we have on some sort of flat level surface, we have an object that is going around in circles, but here you are viewing it, right? So here's your field of view looking out at this thing. Your field of view is from the side. And so this image here is actually representing your view from a side angle. And so what you would see is just simply this object going back and forth. And if I were to have a really terrible, cheesy example, I'm just going to have my little charger here. So I can have, circular motion. But if I set that circular motion in a way to where it's in your plane of view, it really just looks like the object is simply just going left and right in your field of view. And so it turns out that that motion is, in your field of view, that motion is the exact same thing. It is identical to simple harmonic motion. If you could see nothing but this object and you couldn't see the string, then doing this would look the exact same as this, given that, this was on a spring set in motion. So mathematically, we can make them identical. And that's what we're going to be working on here, is setting these two things set equal to each other. And let's kind of look at the conceptual rationale as to why. I do have another video that goes into all of the mathematical derivations of all of these equations. So I'd like you to look at that separately, but I just want to go into a little bit more of the conceptual sort of overview of it. So in fact, let's look at a particular position here that I think is easy to understand to start with. Rather than looking at this spot here, let's look at this spot. When it's right here, when this object is going around and it's right here, its velocity is in that direction. Okay, it's going directly to the left. And I want you to recognize that the velocity along its path, its tangential velocity, is the same, right? If you're looking at it from a side view, that is equal to the velocity here. However, if you recognize, let me switch up colors here. What about when it's off to the side? Okay, when it's off to the side, it has a tangential velocity in this direction, going away from you. And so if it's all the way off to the side, what is its velocity in your perspective? In your perspective, it's going back and forth, right? So it's all the way off to one side. And at that moment in time, it is changing directions from your field of view. It actually has a velocity of 0 at that moment in time. So the tangential velocity here is not the velocity that you see from this perspective. There's only 2 moments in time when it would be. That is when it's here and when it's here. In fact, let me switch up colors back to what I had before. So when it's here and it's moving in this direction, then its velocity along the tangent is equal to its velocity from your field of view. And so it turns out that V max, right, isn't this V max here? This is what I'm expressing here as V max. And V max is the same thing as the tangential velocity in the circular motion, right? This velocity here, this velocity along the tangent, is the same as this V max. Those are one and the same. Okay, I'll let you kind of marinate on that information for a moment as I erase this stuff. Okay, so think about that. Okay, so the velocity along the tangent here is equal to the velocity that you see as it's crossing the middle. And then the velocity on the ends is going to be 0 for your perspective. But let's think about the acceleration for a moment. Your acceleration from your field of view here, the acceleration at the middle, okay, so at this position here, your acceleration would be equal to 0 at that position, versus your acceleration on the ends, okay, so when it's on the ends, the acceleration here would be the same as the acceleration towards the center, the centripetal acceleration. I think I made a pretty ugly A. I'm going to try that again. So this is the same thing as the centripetal acceleration. And let's think about why. Okay, so if I go back up to here, I'm going to draw this same spot. So there is an acceleration acting towards the center, right? However, in your perspective, the acceleration towards the center is perpendicular to the motion that you're seeing. So there's no way that there's any component of the acceleration that is in the same direction as what you're seeing. However, when it is off to the right side, okay, here it is over here, its acceleration towards the center is the same as the acceleration that you see from your perspective here. So these are one and the same. So when it's way off to one side or the other, the acceleration that you see is the centripetal acceleration. So the acceleration max that this thing experiences here, okay, it experiences the most acceleration on the ends. That acceleration max, which is on the ends, is the centripetal acceleration. Okay, so we can relate these things together. So I hope that you guys are seeing how we can relate to this circular motion to simple harmonic motion. And the weird part is, and it becomes kind of neat and interesting actually, is that if I had a box with some sort of spring on it, okay, so let me put a spring on it, and we set this thing set in motion, we allow it to go back and forth, so on one side versus the other. So this is, A and negative A and so on. So it turns out that we can actually express this in the same way. You're like, hey, this would be that, over on the right side, we have a centripetal acceleration. You're like, wait a minute, it's a spring. It's not moving in a circle. Doesn't matter. The math is the same, right? And that's something in physics that you will have to be okay with. That even when I know that that's what's not actually happening, we can express it that way mathematically because the math works. And I know that the math works. And sometimes that's the way things are done. It is because I say it is. How about that? Okay, so that is the relationship between the linear and accelerating motion. You should also recognize that the force is at its maximum on the right and left sides. And in terms of the acceleration, I can even use this triangle that is made here to kind of express that a little bit further. So let me get rid of my marks again. Okay, so let's look at this spot. Okay, this spot here. There is an acceleration towards the center, okay? The acceleration that you observe here for that spot, what is the acceleration that you observe? It is the x component of the acceleration. The acceleration in the x direction, right, is the acceleration that you would observe here. Those are one and the same. Whoa, what'd I do? Okay. Okay. Let's have at it. Let's go to the next. Okay, so sorry, let me just kind of focus a little bit on these equations just for a second. So the velocity at any point in time is equal to this equation. Again, in another video I show where this comes from, but basically just know what these variables are and be able to use it. So velocity is the velocity along the tangent, right? And the V max is the velocity specifically as it crosses the middle. K is the spring constant of the spring, and even if you don't physically have a spring, you can still express it in terms of K. A is the amplitude, maximum displacement, right? Vmax, again, that is the velocity as it crosses the center, or it is the same thing as the the tangential velocity. All right, let's move on and look at some more equations. Again, we're just going to kind of look at these. The derivation can come later. So T, big T being the time period it takes for one complete cycle of whatever this thing is. So if it's something moving in a circular motion, it is one complete circle. The point where people get confused is if it is a box on a spring of some kind. Okay, so let me put this thing on a spring. And this thing's going to go from here to here, and then it also goes to the other side. So I have this thing at the equilibrium. So this is x equals 0. So this would be A, and this is negative A. So I'm going to pull it and go, set it into motion. You should recognize that, I'll make a little ghost image of this box, right, for each position. Right, so it's going to go from one side to the other. So let's say I pull it to the left and I release it here and I set it in motion. It's going to go from here, from the far left to the far right, and then it's going to come back. And the time it takes to go to the far right and then all the way back to the far left, that would be our value of t. That's the time it takes for one cycle, so seconds per cycle. A lot of people get confused by this, and they will make t equal to the time it takes to go from one side to the other, and that would be not correct. You have to make it equal to the, it has to be one complete to and fro. Okay, so just to be clear on that. And since f is equal to 1 over t, we're just doing a quick substitution, and we can express it in this way as well. This equation, I think that it might be kind of helpful to, memorize it. The way they often would get used in the AP test, I should actually look. It might actually be an equation on the AP equation sheet. I'll have to look. But the way this sort of thing often gets used is a question might in some way relate, hey, if you change k, let's say you double k, how would that change the time period? Okay, so you should know that it would change it by 1 over the square root of 2. That's how it would change, right? So if I were to double this, or if I double k, then t would change by a value of 1 over the square root of 2. Right? That's a square root symbol there. Okay. So it's things like that you should recognize. Let's look at more equations. Again, the derivation of these and where they come from is in a separate video. So as I said, we can express circular motion to a linear motion. So even if we do have a spring, we actually can, you're like, where did k go? Right? Where did the spring constant go? Now we have circular motion. I can be looking at a spring and yet still express it as if it is circular motion. That is angular velocity. That is radians per second. Don't forget that. Okay, so this essentially comes from the idea that, if we're measuring this angle theta, that the adjacent side of this triangle is going to be the cosine, right? We're going to use cosine for the adjacent side. And so that is what allows us to get the angular velocity, essentially, for this object. And again, it's just a matter of being able to use these equations and understanding, generally speaking, where they come from is pretty much what's needed here, what's fundamental. So why is it that we are relating this in terms of circular motion? Like, where does this come from? And here's kind of a good part where it all comes together. If I were to take a spring and set it into motion, so it is moving up and down, simple harmonic motion, and I take a big piece of butcher paper and I drag it across, and I've even done this in the classroom where I put like a marker or a pencil on the spring. As it makes a mark on the paper, right, the paper is being dragged across at a very consistent velocity, it is going to make a sinusoidal wave. And those of you who are paying attention might yell at me and say, no, that's a cosine wave. Well, just adjust it by 1/4 wavelength. It's sinusoidal, okay? Get off my back. So this is essentially a sinusoidal wave, and so we can relate any sort of wave motion as being related to simple harmonic motion, and we can also make it related to circular motion, which is why when you look at any sort of wave equations, we often will actually have omega in the equation, because that is the relationship between the circular motion, simple harmonic motion, and then in turn wave motion. So these things are all interconnected because the math comes together and marries nicely between all of these concepts. I think I have one more slide for you, some more equations. So these are the equations that we would use with this wave motion and relating it to simple harmonic motion. So this is going to relate the displacement, velocity, and acceleration of the simple harmonic oscillator as it creates a wave. So this is the point at time it has got its greatest acceleration and least acceleration. Here at this position, it is at 0 acceleration. Let's make sense of that. So let's focus on this point right here. The acceleration is 0. When is that happening? That's when it's crossing the middle, isn't it? Let's say it's moving in that direction. It has a very high velocity, but the acceleration is 0. The spring has no tension on it either way. It is at the equilibrium position. It is at its greatest velocity, but the acceleration is at its minimum. And so that would relate to this position right here. Okay. So we will get more into waves. We will get more into sound. These are all things that I'll do separately from this. But hopefully this is a good little introduction on how we can have this relationship between circular motion, linear, simple harmonic motion, and also with wave motion. I think I want to end on one last thing if I can, but I'm just going to draw it out because I don't want to give you the equation, at least not as of yet, because I have a lab where we kind of explore this. But if we have a pendulum that is going to swing back and forth, and I'll create like a little ghost image of it here. Okay, so a pendulum can express simple harmonic motion if the angle is small. As the angle gets larger, okay, if the angle is very small, it will have simple harmonic motion. Of course, this is assuming that all the mass is at the center, at the end, and then the string is massless. And so we set it into motion, and if the angle is small, this exhibits simple harmonic motion, where the force is proportional to the displacement. However, when the angle becomes very large, it no longer really exhibits simple harmonic motion because that relationship is no longer proportional between force and displacement. So at what point is it no longer simple harmonic motion? It's typically 5-7 degrees, something like that. And the reason being is you start to get beyond about 2 or 3%. I think really beyond like 5% is really about where they start to look at it. Because once it's deviated away from simple harmonic motion by about 5%, then that you're at a point to where even the classroom setting, we can create an experiment where we can actually start to observe that it's not the same. And so once you get to that point where it's no longer negligible, like that's it, I can't ignore it anymore. It's no longer negligible. I can't pretend like it's actually simple harmonic motion anymore. Well, there you go. So at small angles, it is simple harmonic motion. We will do a lab because it is important for us to recognize the relationship between the mass that is on this pendulum, the length of the string of the pendulum, and the period of the pendulum, how long it takes for it to go back and forth. Don't forget, it's the to and fro is the time period for one cycle. So with that, we will explore that more, and I think that'll end things in terms of the video that I'm making on that. So that'll be it.